Hi, Sophia. And Elisa, she's going to be late. I mean, 10 minutes. She will join us later. Lecture 50. So, chapter 7, techniques. So the, oh, I forgot to do this one. So the first technique comes from the rule we learned before, the product rule. So this is the one of the most important methods. Very important. But it comes from a very simple rule. By part. We will say why it's called by part. What does that mean? So Sakina, you were not here. What's the rule for product for this product? Okay, very nice. Okay, so this is a very useful rule when we take a derivative, but also lead us to the very important technique, integration by parts. What does that mean? It means we have this equation. So the integral of this will equal to the summation of the integral of the two, right? Okay, the integral of the left-hand side. This will be the integral of this. Okay, so for these three integrals, this one, the derivative, then integral. Okay, so what's this? Think about it. What's this? Integral of the derivative. So the integral of the derivative, this is by the fundamental theorem of calculus. So integral and the derivative, they cancel each other. This equals to fundamental theorem of calculus, FTC. Now we're left with two integrals. Normally, if this is the one we are looking for, we want to convert this to something simpler. So one of them is simpler. So we can use the simpler integral to find this more complicated integral. Okay, we will see more examples. So suppose this is a more complicated one. Suppose this is more complicated. Then this integral equals to okay. So this in most cases is relatively easier to integrate. If we can integrate this easier one, then we know what the integration of this complicated one is. So this is called integration by parts. So which one we integrate? integrate this part or integrate this part. So this is the name of this technique, integration by part. This is what we call integration by part. Very useful for a simple practice. A simple practice. The integral of x e to the x dx. Okay, so we have done this last time. So Sophia knows. I want to check with Sakina. How do you integrate this one? I know. So without this technique, the only method we know is the fundamental theorem. Fundamental theorem of calculus. That's how we do the integration. However, if we go over a list of functions, there's no function whose derivative is this. So first, we want to try this fundamental theorem of calculus. We need to find a function whose derivative is, it's not easy. It's not on our list. We have sine, cosine, exponential, power, but we don't have this one. So what we do is we want so now we see this one is complicated to integrate. We will apply this integration by part to convert it to something simpler. We will see what the simpler thing is. Okay, so this doesn't work. Not easy. So let's go to the IBP. IBP. Good. Integration by part. So this will be our f. This will be g derivative. So in our setting, fx is g derivative is x. Okay, so now what's the derivative of f? And do you know an antiderivative for g? Now you see that this is what called easy. With this, let's apply the formula. So by the formula, x e to the x dx. So I'm going to copy the formula. Gx minus f derivative gx dx. Okay, I do nothing but copy the formula. What is f? What is g? E to the x minus, what's f derivative? 1. What's g? E to the x dx. Okay, now could you tell me what the integral is? Integral of e to the x. Yes, easy. Yes, easy. Okay, so now see the integration by part, what it does. We want to do this complicated integral. By this technique, we only need to do this slightly simpler one. Then we find the indefinite integral. So it depends on what method you use. Previously, we have this method, the fundamental theorem of calculus. We want to find the integral. Let's go to find the antiderivative. The antiderivative gives us an integral.
The integral is the antiderivative.
Yes. So that's the first method. So the fundamental theorem, what it tells us? Fundamental theorem. So if the derivative is f, then the integral is, this is the fundamental theorem. We want to find the integral. Now we will try to think what the derivative is f. Then this is our integral. That's the fundamental theorem. So it connects the integration with derivative. If we can trace back the derivative, we have the integral. Okay, so that's the fundamental theorem. However, in this one, it's difficult to trace. There's no way, we don't have the formula. We don't know how to trace it. So we use a new technique called integration by parts. This is complicated, but this is easy. So this technique allows us to compute this complicated integral using this simpler one. The simpler one, we apply the fundamental theorem, we find the in-depth integral, then we find, with this part, we find it. Okay, so now let's check our calculation is correct. Okay, let's take the derivative of this. X, e to the x, e to the x. Let's see, what's the derivative? Okay, one by one, secant. How do you take this derivative? X, e to the x, how do you take this derivative? The product rule, right? So what's the derivative? And subtract, and plus the constant. If it's x is 1, if it's a constant, it's just 0. Now they cancel each other. So we have x to the x. And this is what we had in the very beginning. So that's so now we verified the integral is this by the fundamental theorem, because the derivative is this one, we can recover the integral. Okay, so that's our first example. A second example is very similar, but slightly different. Okay, Sophia, from the list of the derivatives, do you see this one? X, cosine x. Have we seen something like this before?
No.
No, okay. So it's not in our list. We cannot apply the fundamental theorem directly. What we do, we will apply this integration by part. Again, integration by part. This integration by part, this will be our f. This will be g derivative. Okay, Sophia, what fx is x? What's gx?
Sine x.
Okay, because the derivative is cosine, we can get gx is sine x. Now we can take a derivative easily. Is 1. Okay, so now let's apply the theorem. So my first step will be copy the formula. That will be always my first step. Fx gx. And check the formula f derivative gx dx. Okay, then we substitute f. We know it's x. G sine. F derivative we copy is 1. G is sine x sine x. Okay, Sophia, what's the integral of sine x?
It's negative cosine.
Yes, negative cosine. Negative cosine. Okay, simplify. Okay, so another illustration how we apply this integration by parts to find this integral. Oh, Elisa, you're back. You're here. Oh, you're on your car. Okay. Okay, cool. Okay. Okay, so now let's check. Okay, so Kina, how do we verify this? Okay, let's take the derivative. Take the derivative of x sine x. I'm going to check with Elisa. Can you hear us, Elisa?
Yeah.
Okay. Oh, okay, that's fine. What's the derivative of this one? X sine, the product rule.
X cosine x times sine x or plus sine x.
Uh-huh. And
And
cosine x.
plus, plus sine or negative sine x.
And what's the derivative of c?
C.
C is constant.
Oh, 1.
0, not 1. Okay. Now this sine cancel with the sine. We have x cosine x. And this is the integrand we started with. Okay. Sometimes it's not that easy. It's not that apparent. How do you apply this method? This one is not, that's number 3. Okay, let's think about this one. Okay, the indefinite integral of logarithm x. Is it 1 over x? Sakina? No, why? So yeah, this is the derivative, not the integral. Okay, this is a very popular, very common mistake. When we say this, someone will just give 1 over x, but that's the derivative, not the integral. Okay, so how do you find the integral? Okay, first we try the fundamental theorem. If we're trying to apply the fundamental theorem, we're looking for a function. For the derivative is logarithm. Then we go over our dictionary, our knowledge, our head, or something. There's no such thing. So again, let's try the integration by part. We try the integration by part. To try this, we wanted to identify fx g derivative x dx. So the product of two functions, here we only have one x function. Should this be f or should it be g derivative? Okay, so if this is the g derivative, we have to find the g, and that's the initial problem. This doesn't work. So let's try to make this fx equals logarithm x. Now, if we want to match these two integrals, I match the one function. Now, what is the g derivative? Okay, that works. G derivative is 1. And Sophia, what's the derivative of f?
1 over x.
And could you give me a function whose derivative is 1?
X.
X. All right, now we have our two functions. Let's apply the formula. Okay, Sakina, what's the formula for this integration by part? Mm-hmm. Similar, it's a complement of this one. So here's f g derivative. We have f derivative g, a complement. Okay, now let's plug in what do we know? Fx is logarithm. Gx is x. F derivative 1 over x, gx dx. Okay, so this will be x logarithm x minus. If we simplify 1 over x, they cancel each other, integral of 1. What's the integral of 1? That's the derivative. What's the integral? So something whose derivative is 1. Okay, that works. Okay, again, by this integration by parts, we find this indefinite integral. Okay, how do we check this? So okay, now what do we do? How do you check this? Take the derivative. Okay. Let's check. The derivative. Okay, by product rule. Um, okay, so there's some practice of this integration by parts. If we compare these examples, the first one, x e to the x, we identify f and g derivative. In this way, f derivative, it becomes simpler. G derivative, not much more complicated. Okay, so in this way, we reduce the difficulty of the integrals. From this one, two difficult part to one part not more difficult and one part much simpler. Similarly, this one, x cosine x, we identify f and g. The reason for this is the derivative of f becomes simpler. The antiderivative of g is not more complicated. Cosine, sine, they're the same level. So this one is more interesting. We have only one function. So what we do is we identify the derivative of the one. So the derivative is one, slightly more complicated, but this part becomes much more simpler. So overall, we gain something. So from here to there, we gain something, becomes simpler to integrate. Okay. Now let's have another practice. So here, what's the key point? Key point, if we want to take the integral, as long as we know the derivative. If we know that we can find the derivative, we can find the integral. For the next one, if we can find the derivative, it will help us to find the integral. Arctangent. Okay, first step, let's recall what's the derivative of arctangent, tangent inverse. Okay, who can recall this formula? Sophia and Lisa and Sakina. The derivative of tangent inverse. Sophia, do you remember this?
Um,
It has been a while.
Wait, it is.
the fraction. We have 1. What's the denominator?
Square root? Or,
Okay, that is derivative of arcsine. It's
oh,
similar. Okay. Derivative. Okay, let's see. How did we find this derivative? What method did we use? How did we find this derivative, Sakina? Okay, we use this implicit differentiation. Okay, so let's maybe briefly recall this implicit differentiation. This is the same as tangent y equals x. So again, we want to find the derivative of the inverse function. If we can find the derivative of this function, that will help us. Okay, so again, what's the derivative of tangent? Secant. Because y is the function of x with the chain rule. And this is the derivative of x, which is 1. So y derivative, 1 over secant squared. And secant squared is 1 over 1 plus tangent squared, so which is x. Okay, that's how we find the derivative using implicit differentiation. To find the derivative of the inverse function, we set up the equation, then by the inverse property, tangent y is x. Then implicit differentiation and substitute back to x, this gives us the derivative. Okay, now we know the derivative. We want to find the integral. Okay, let's identify f g derivative. Sophia, what would you say for f if we want to apply the integration by part?
um, we would,
Let's compare with the previous one. For logarithm, we identify this with f, and we make up this derivative as 1.
tan inverse.
Okay, so in this case, I want to set this to our f. So the derivative will be 1. We just find the derivative. It's 1 over. And we have found the antiderivative of this. That's easy. That's x. Okay, now we are ready to apply this integration by parts. Okay, maybe I will give a few minutes to do this yourself and let me know when you finish. You can answer yes, maybe enter finished in the chat, so I know you finished. Okay, Sakina, uh, you guess what will be my first step? Okay, very good. Very good. The formula. Okay. And is that your first step also, or you have a different first step? Okay. Fx, gx, f derivative, gx, dx. Okay, so now we have this fx f derivative gx x dx. Okay, it's x tangent inverse. Now, how do we integrate this one? Lisa, what would you do? She's on her car. And Sophia, do you have any idea how to integrate this one?
Um,
1 plus x squared on the denominator.
we could
Substitution? Do we use substitution here?
maybe
Okay, let's try. If we have this u equals 1 plus x squared, what's the du? What's the derivative?
2x.
2x. So du. Okay, let me check with Sophia. The derivative is 2x. Now what's du?
Um,
We still have 2x. Is that all, or have something else?
2x plus c.
Okay, so
Oh.
now so that this new notation, this is the derivative, and the numerator and denominator, we can treat it as the quotient of two differentials, du over dx. In this sense, du will be this time dx. So from derivative to differential. Okay, so the different roles. This differential. Okay, so we found that if we replace this by u, du is 2x dx. Here we have only x dx. So what do we have? If I want to replace it by du, should I put something? If it's 2x dx, we will have du. But here we have only one, we have this 1/2. Okay. So now with substitution, it will be 1 over u, 1/2 du. All right. So this is what we have. Use substitution. X tangent x. All right. So what's this? 1 over u du. So Kina, what's the integral of 1 over u? Something whose derivative is 1 over u. lnu, yeah, that works. This will be x tangent. Okay, after we are done with the integral, we will switch back to the x variable because u is 1 plus x squared. Switch back. You can see the indefinite integral of this arctangent is quite complicated. You have this part and a kind of unrelated part. If this is correct, does this sound correct? We should check. Okay, I will give you a few minutes to find the derivative of x arctangent 1/2 and see if you recover our initial function. Okay, let me know when you are done. Derivative of x arctangent. So the product rule. So we have 1 product rule minus derivative of chain rule. So this will be logarithm chain rule x. And we can see they cancel each other. This one has 1 over x squared over x squared. 1/2 2x x. They are exactly the same. The derivative is what we started. The very confirmed the computation over there is correct. It's a little bit long because this is not an easy integral. Without this method, we don't have no idea what it is. And it's very difficult to guess this formula because this integration by part. So for these examples, we only need to do it once. Sometimes have to do it 2 times. Okay, let's try next one. X squared e to the x. Okay. Let's try this one. Okay, what? So let me choose the number. Number 5. Okay, we want to apply this integration by part. Okay, Sophia, for this one, what is f? What is g? And what's the derivative?
That is x squared.
And
G
g
is e to the x.
From here, what's f derivative?
2x
What's the antiderivative for g?
g ex.
Okay, nice. Okay, so again, this choice make the derivative simpler and the antiderivative not any complicated. Normally, so the antiderivative will be more complicated. If it's more complicated, we'll try to avoid it. So in this way, we can continue the integration by parts. It will be fx gx f derivative gx, which is x squared e to the x to x e to the x dx. And this is something we have done before. We can look up the formula and we get okay. Now we distribute, we get we should have minus 2c, but our c stands for integration constant, so we can relabel it. Since c is an integration constant, it's not a number. Okay, now let's try if we got the wrong direction. What happens? What happens if we went to the wrong direction? If we identify this f x to e to the x, g derivative is x squared. Okay, so now what's f derivative? Could you give me an antiderivative for g? Whose derivative is x squared? Should be some power, some coefficient. What's the power? So if we take a derivative, the power will reduce by 1. So something subtract 1 get 2. X cubed. And what's coefficient? If we take this derivative, we get 3x squared. We want to cube this 3 to 1/3. Okay, now let's compare these two setups. The first setup, this one not complicated, but this becomes simpler. So we get a simpler integral. If we go this direction, what we get is fx gx f derivative gx. You can see this one is more complicated than what we started with. So whenever you get something more complicated, you know you went to the wrong direction. You get the roles of f and g reversed. So if it's more complicated, you stop, you go back to adjust your setups. Okay, I got Alisa's message. And Sophia, any questions about this integration by parts?
No.
Okay, so you have more practice about this. More practice will help to see which is the right direction. The right direction is always something simpler, not something more complicated. That's the key point of this integration by part. You want to convert something complicated to something easier. Okay, wrong way. I'm not sure what this is. Okay. Okay, another technique. Trigonometric integrals. Okay, we'll start with something easier. Okay, Sakina, first one. Sine x, normally we put a c over there, integration constant. And Sophia, second one.
Negative cosine
Mm-hmm.
x plus c.
Okay, so that's the first case. Then we got slightly more complicated. Cosine square x. Okay, Sakina, how do you integrate this? Cosine square. We know how to integrate the cosine, how to integrate the sine. Could we reduce the square to something? So this time we need this double angle formula. We use it to find the two squares. We call it double angle formula. Okay, Sophia, do you remember this formula for cosine 2x?
Yeah.
Uh-huh. Okay, give me one. There are many, give me one.
1 minus 2 sine squared x.
Correct. So Kena, could you give me another one similar to this? Okay, very nice. Okay. Okay, so I will combine these two. It will give me an expression for cosine square. Let's isolate the cosine square from this equation. Okay, so cosine square x 1/2. Okay, now we can continue this integration. Cosine square reduced to cosine 2x. Okay, so let me separate to be 1/2. The integral of the addition is addition of the integral. First one easy. I will put the c later, but before that, let's figure out an antiderivative for cosine 2x. Okay, so Kina, what do you think? Antiderivative for cosine 2x. Uh-huh. And Sophia, so something whose derivative is cosine 2x.
Mm, mm,
First, the cosine. Whose derivative is cosine? We know it's sine. Let's try sine 2x. Is this it, or we have to modify it? Okay, well, it will be there. Okay, let's put C over there. First, let's check sine 2x. If we take a derivative, Do we get this or do we get something else?
I think that's okay.
So sine 2x, okay, Sophia, when you take a derivative, what do you get?
Cosine 2x?
And chain rule.
And you get 2.
Yes, we have 2 over there. So if we have only sine 2x, the result will be 2 cosine 2x. So how do we make corrections? We want to kill this extra 2. How do you kill this 2? We will divide it by 2. In this way, we anticipate there will be another 2 because of the chain rule. So we put 1/2 over there to kill that. Okay. Now the result will be 1/2 x. 1/2, 1/2, 1/4. And 1/2 c. Again, we will label this as c. It's just integration constant. Okay, so we have done it for cosine. We will give you a few minutes to do the same thing. Use this formula for sine squared. Okay, okay, sine squared. Okay, think about this, how to find the integral of sine squared. Okay, where do we start again? What's the first one? 2 sine squared equals to 2 sine squared. What's the okay? So we divide by 2, we get okay. So the integral will be this. Again, we can put on this 1/2, and the integral of the difference will be the difference of the integrals. And we have done this exact integrals over there. We have plus, the only difference is minus. So it will be this minus it. Okay, I'm going with C. We have relabeled it. Okay, so let's have 5 minutes break and we'll be back at 11. We have a break, okay. So we have this, the integral of the squares. Next, let's go to the cube, see what happens. Okay, let's try to think. What method could we use if we want to integrate the cube? So previously for the linear, the first order, easy, well, you know the formula. For the square, we have to use this double angle formula. So completely different method. Now cube. Do we use the cube formula? Cubic angle, like the triple angle formula? That's too complicated. There's a very simple one. I'm going to continue this one. We are going to split this cube into an even power square and a cosine x dx. Okay, then we want to use the substitution. So du, we want to treat this as a derivative. If u derivative is cosine x. Okay, Sophia, what's u?
Sine x.
Sine x. So now I'm going to write this as use this substitution. Du. Now cosine square. Could we represent this as a function of u? So okay, now what would you do? U is sine x, cosine x. What would you? So how do we go from cosine square x to some function of u? Okay, so we have this cosine square. So u is sine, what's u square? Easy, sine square. Now the difference between cosine square and sine square, they're very close. What's the connection between them? If we add sine square with cosine square, what do we get? Okay, that's what we need. So cosine square is 1 minus sine square. And we know sine square is u square. 1 minus u square du. Okay, so, Sophia, how do we integrate this? The integral of the yes, u
Minus
2.
2.
So first fix what's the power?
2.
You take a derivative, you get a square.
Oh, it's 1/3. Or
Okay, yes, it will be 1/3. No way. 1/3 u cube. Let's see. Then we switch back to x. U is sine x. 1/3 u cube sine cube. You see, another method to integrate the cubic power. We split, then use substitution, integrate, we switch back to x. Okay, let's try the same thing or similar thing for this one. Okay, see what's the first step? How do we integrate this sine cube? Sophia, what would you do?
sine
Compare with,
squared
okay, yes.
x times sine of x.
We split all the power to even with sine x. Okay, now let's do substitution. u derivative is sine x. What's u?
Negative
Negative
cosine
cosine.
x.
Okay. So now we continue. So this will be negative du. Okay, how do we deal with this factor, sine square? How is it related to u?
Mm.
So sine square against 1 minus cosine square. One minus. How do we convert this to u? Sophia?
Negative u squared.
Just yes, negative u squared is squared to u squared. This negative du, I can put out a negative sign. Okay, then the integral, it will be negative u minus 1/3 u cubed. Let's see. This is negative u. And we switch back to x. Negative of cosine x. Negative cube. Okay. Okay, any question about this one? No. So we applied similar approach for the cubic power. We split to even, odd. Then this reduced from a trig function to a polynomial. We know how to integrate the polynomial. Just match the power and the coefficients. Then we get to the integral, switch back to x. Okay, let's make a jump. Fifth power. Okay, two of you. Which one do you want to try? Cosine 5 or sine 5? Doesn't matter. Yeah, that's the correct. Okay, doesn't matter. Let's try cosine 5. Okay, Sophia, first step, what do we do? For the fifth power,
You would split it.
split cosine 4x cosine x dx. This will be our u derivative. From there, we see u must be sine x. We use the substitution du. Okay, this cosine fourth power, how do we convert this to sine and how do we convert it to u? If it's cosine square, we have
You
this.
split it again.
Okay, so this will be the square of the square, right?
Oh,
That works. It's essentially the same thing. It will be cosine square square. Cosine square. Okay, Sophia, what's cosine square?
u
Uh-huh.
derivative. Oh, 1 minus, wait, what?
One
U
minus, yes, one minus
squared,
sine square, 1 minus u square,
squared.
square d. Okay, again, from a trig integral to a polynomial. And that's easy. We just expand and integrate the term by term. to a new page. U cube fifths. Then we switch back to x. X is sine. Okay. Okay, now you can imagine what happens if you have sevenths. Again, we split to the cube, again, from a trig function to a polynomial integral. Okay, okay, so for this, the sine or cosine. Next, we have a combination of them. Let's try a combination of them. And more generally, we have cosine nx sine mx. The rule is that if one of the powers is odd, like what we had over there, we split and use substitution. Okay, so that's the rule. If one of m n is odd, use substitution. So what here, this is odd, so we will split to cosine square x sine 4x, the leftover cosine dx. Substitution, so this will be our u derivative. U will be cosine x sine x, sorry. Okay, I will give you a few minutes to think about this. How do you convert this to the integral of a polynomial with the substitution u is sine x? Okay, Sophia, what would you do?
It would
First,
be
okay,
cosine,
yes.
It would be u squared.
So u is sine x. The cosine square, how do you convert this to sine?
You can do u squared minus 1.
1 minus u square.
Oh, 1 minus u squared, yeah.
And what about sine fourth power?
u4.
u4, nice. Okay, again, from a very complicated trig integral to a much simpler polynomial integral. Do you agree? As this is much easier to integrate than this one. So what do? We just expand and we integrate them one by one. u4, u6, du. Fifth, seventh. Switch back to x. Okay, so you can see to integrate this trig function with sine and cosine, the key, maybe one of the keys, one of the approaches to use substitution to convert it to a polynomial. Then we integrate and we switch back to x. And try another one. Let's try. What happens if both powers are even? If both of them are even, so we use this double angle formula to reduce the power. And eventually, either the power is low enough, you can integrate directly, or you get one of them being odd equal to 0 until maybe 2. One of the new powers. Okay, so this is about sine and cosine. The main technique, even this, it looks very complicated. But with the substitution, you get something much simpler, and we switch back to x. Sine, cosine. Next, we do another pair, tangent and secant. Okay, step by them one by one. We start with tangent. Okay, Sakina, tangent x. Do you know the derivative of tangent x? Secant square. And previously we found the integral of arctangent. How do we find the integral of tangent? So this we use the definition of a tangent. It's sine over cosine. So we use substitution. Substitution, this is u derivative. So u must be negative cosine. Use the substitution to get negative u du. Negative u du, negative. Okay, so again, how do you integrate this? One over u du. And Sophia, what do you see?
Log.
Something, yes. Okay, log. Because u may be negative, so we use absolute value, as long as it's not 0. Then we switch back to x. Okay, so this is the integral of tangent x. Okay, next one, tangent square. Then next page. Enough, finish. Okay, so it's similar to what I have done before. For the first order, we use substitution. Second order, we need some formula. What formula do we have for tangent square?
Sec 1 plus secant square.
If we add 1, we get secant square. So this
Yeah.
will be secant square minus 1. Okay, the integral of the difference is the difference of the integrals. Okay, integral of secant square. Something for the derivative is secant square. Tangent, you just said this before and said it again. You use tangent x. Okay. So we find the integral of tangent square. Okay, let's go another level. Tangent cube. Okay. Again, it's similar to what we have done before for cubic power. Sophia, what was the trick for the cubic power?
You split it?
Let's try split. Tangent square tangent x dx. Okay, so here I will use the same trick, tangent square secant square minus 1. So this is okay. So again, the integral of the difference will be the difference of the integrals. Secant square x tangent x. Okay. For the first one, we know the derivative is of tangent is secant. So we can use substitution. U derivative is secant square. U is tangent x. Use the substitution, we get U du. And tangent x, we have found it in the first step. Let's just copy the result. Negative logarithm of a sort of cosine. Negative, so it will be plus. Because we have the integral sign, so we'll put the constant later. And this integral is much easier to integrate. U du is just 1/2 u squared. Then we switch back to x. U is tangent x. Okay, now you can see for these integrals, we have different techniques in different situations, but they are similar. We use the trig identities repeatedly. Either it's the Pythagorean theorem, cosine squared plus y sine squared equals 1, or we use this double angle formula. Either way, we convert this to something simpler and we find the integral. And the next time, we will start with secant and the mixture of secant with the tangent. This will finish this trig integrals. Okay. All right.